We present an architecture with the specific goal of providing support for continual feedback about uncertainty in user interfaces. Consider this touch diagramming tool inspired by Igarashi's interactive beautification. Users add shapes to the canvas by dragging out a bounding region. Multiple shapes are possible. The application guesses the most likely shape based on past actions. When the user hesitates, the application shows an best list highlighting changes. The user may then select an alternative by tapping on it. Shapes and lines may be dragged. When an item is being dragged, a trash can appears at the bottom of the screen. Dragging to this area removes the item. Of course, if the user just wants to put the item at the bottom of the screen, she can select this alternative as well. In addition to being dragged, shapes can also be resized. When adjusting lines, endpoints snap to targets. Here is a demonstration of the features of this application. Such an application would be very difficult to implement in a conventional interface framework. With our framework, both the tracking of interface alternatives and the rendering of these alternatives to communicate uncertainty are handled by the system. Interface developers only need to worry about specifying the operational logic of interactors and about rendering a single alternative to the screen. Behind the scenes, our architecture takes a probability distribution over interfaces, identifies differences, reduces this to a smaller representative set, and fuses this list of alternatives into a single interface which is then displayed to the user. We provide a library of several different feedback techniques which developers can use when making interfaces. Developers can then pick which technique they want to communicate uncertainty. By changing these algorithms, drastically different interfaces may be generated without requiring any changes to the layout or rendering code. For example, we experimented with several feedback techniques in a predictive menu system we developed. First, we tried overlaying alternatives using opacity. We found this helped inform novices of possible completion, but provided no way to accelerate selection. We also tried a traditional best list. Users could select alternatives using mouse or keys. However, the items in the list were difficult to interpret. Finally, we settled on a more compact best list rendering. One family of techniques we implemented is best lists. Here are a few more examples of this technique. When a user executes a touch gesture and several interpretations are likely, the system allows the user to disambiguate. The best list can show just the components that changed, the entire interface, or show the entire interface and highlight changed components. Selecting text can be cumbersome on a mobile device, requiring a press and hold because of ambiguity between text selection and scrolling. This demonstration tracks the likelihood of both the text selection and a scroll, using a finger's motion to guess intent. If the guess is incorrect, the user may pause, causing an alternative to appear on the screen. She can then select this alternative and continue scrolling. Another example feedback technique in our library is to overlay alternate interfaces, adjusting how each alternative is presented to communicate likelihood. In the following demonstration, we can drag icons to different targets in order to perform different actions on them. The probabilistic version of this demo attempts to guess which target the user wants to use and adjust the likelihood of each target based on distance. We can then overlay these alternatives and use opacity to communicate likelihood. In addition to using opacity, we can modify other drawing parameters to indicate likelihood. For example, changing scale makes changes in likelihoods more salient. Notice here that while the targets are changed using scale, the icon likelihoods are still using opacity. We can see the same behavior when we modify blur based on likelihood, and even draw progress bars.